All right, everybody, welcome to Young African Scientists. This is a machine learning course, and we are running this. This is lecture 9. And today marks the end of the official lectures. The next lessons that we are going to have are all going to be projects. So you are officially completed all the lectures. Our next lessons are going to be projects that you're going to do with the instructors, and you're going to submit them for your certificates. For now, we're going to give you certificates for all the lessons that you have attended. We have all the attendance sheets, all the attendance for all the days. So we will check through all the attendance. The ones that you are able to make it, we'll give you certificates for those ones. We have changed the rules a little bit. And so everybody is going to get certificates, but it will depend on your attendance. So the day you are able to make it, we are going to give you certificate with that date. If you think that there was a day you came, you didn't mark attendance, you can contact us, and then we'll see how we can make the arrangements. But we are going to certify you based on how many days you were able to come and the lessons you were able to attend. So I'm passing you on to Trustin, and Trustin is going to take us through. Please, it's 1 hour, 30 minutes. The teachers are notorious for going overboard. So please, let's try and work within the time. All right, Trustin, please take over.
All right. Thank you so much, Dr. Tabiri. I'll try as much as I can to stick to the time. I think it's really hard. These are really heavy topics to just cover in 1 hour, 30 minutes. And then I have the coding aspect as well. So, but I'll try my best. Someone sent a message. Okay. Okay. All right. I'm gonna proceed to what I have to teach. So today I'll be talking on speech recognition, natural language processing, transformer, and LLMs. And I must say, before I even proceed, that these topics are sort of very closely related to each other. We have, speech recognition, making use of natural language processing. We have transformers and LLM. So we also have what we call foundational models, which are, LLMs are a type of foundational models. And then speech. Mohammed, if you could mute your. Okay. So speech recognition is an aspect of natural language processing, basically using a computer to understand human speech. And then transformers is a sort of architecture that's embedded in this natural language processing. And then large language models, which are mostly comprised of transformers, are already trained on a large data set. And so they have a foundation, they have a background. And so when you want to apply it to your own data set, it doesn't start from scratch. It has a foundational knowledge and things like that. So these topics are sort of interchangeable amongst themselves. And so we'll just go over some of the main concepts around these topics. All right, so my name is Dr. Trusting Nikwe. The topics will cover the first part. So it'll be in 2 parts. The first part is speech recognition. I'm going to talk very briefly on this because going into details can be quite complicated. We'll probably have to go into like some understandings around acoustic models and how to use some electronical processes to extract features from speech. So I'm going to talk very briefly, and then I'll go more into natural language processing, where I talk about feature engineering, where I talk about sequential modeling. I talk about the trajectory of sequential modeling from GNNs to transformer architecture, and then we'll see a coding example. So natural language processing, when I'm talking about the speech aspect properly, is generally how to make computers understand your speech. So I could take a speech, a recorded speech, and convert it into what we call a spectrogram, and then pass it to a transformer model or a pre-trained transformer model, which is what we call a large language model. So for example, I have a text data or speech data. So speech data is first converted to text data. I'm using a speech to text converter. In that speech to text converter, what essentially, to summarize what it does is this speech that you see in these bars like this, it uses what we call mel frequency, septral coefficients, something like that, to convert this text to sets of features. So for example, if you say a certain word, that word can be converted to a form of numbers. If you could mute yourself, that'd be really nice. I don't know whose thing is. All right, so it's converted to text, and that text data is eventually passed into a model. So this is very summarized description of what happens. There's definitely things that happen in betweens that are not captured here. So why does language matters to computing? Human language is the most natural form of communication. For computers to use human language, it requires a structure. And so natural language programming is just sort of trying to bridge the gap between this, or trying to create a form in which human language can be converted to structure where computers can actually understand it. So we see some example use of these in what we call voice assistants. For example, in your iPhone, you can say, "Hey Siri," or Google phone, Alexa, things like that. We can see in translations, for example, where you actually pass an English word and you can say translate it to a Chichewa word, which is a language in Malawi, or convert it to tree in Ghana. So you could use natural language processing. You type in an English word and then it translates it to the language. I must say, though, that that conversion is not always very accurate. So if you want to send a translated word to someone who doesn't understand English, you have to be careful so you don't send the wrong thing. And then we have chatbots. I know a lot of us are very conversant with things like ChatGPT, where we type in text, and then the computer is able to understand that text, and then generate output for us. So Copilot is another example. Gemini is another example. Claude is an example. So these are common chatbots that we have. Basically, you're chatting with it. And then we also have what we call sentiment analysis, where you try to understand the sentiment in a sentence. For example, I am happy. So the sentiment there is positive. You could say it's positive. I am sad, negative. I don't know how I feel, neutral. So we can apply computers to understand this kind of text, to be able to tell us a sentiment attached to that text. So let's go into speech recognition properly. Speech recognition is essentially the process of converting spoken audio into text. This image just summarizes this speech recognition approach. I'm not going to go into very much detail, and I think I'm just going to stop on this image, but I'll explain this image. So essentially, how speech recognition works is you speak, you have an audio capture. So a microphone records your speech. And then when you want to actually pass that speech to computer, you have to do some processing. So things like that speech. So when you talk, for example, now that I'm talking, there's a lot of background noise. You may not hear it, but there's an air conditioner on right now that is in that sound. So if I speak and I'm passing that speech to a computer, it's very important that I eliminate that air conditioner noise, which doesn't really benefit the model eventually. So that's an approach, right? Eliminating the noise. So that's what we call signal processing, where you remove the noise, things that are not important. After that, it's what we call feature extraction, where each word or each sentence I make has a unique set of features attached to it. So one approach to convert these signals to features is what we call MFCC, which I mentioned earlier. Male frequency septural coefficients is an electronic way to convert that signal to extract features from that signal. There's a mathematical approach to that. If you're familiar with things like Fourier transform, things like that. So MFCC is applied to the signal that Fourier FFT has been applied to, and then you come up with a set of unique features for that. Then after those features are now passed to what we call an acoustic language model. So that acoustic language model essentially compares the phonemes rather. Phonemes, for example, A, A, B, K. Those are phonemes, right? So it matches those phonemes to actual text. So that's the speech to text conversion, right? And then, so that's a modeling on its own. And then it's now that's conversion to text. You could say that's encoding, and then the decoding aspect is where we now we're able to predict words, or we're able to generate sounds and things like that. So this is a very high level, and there's definitely more detail into this. I don't think the time we have will be enough to capture all the details. All right. So this is sort of the high level approach for speech recognition. I must mention that in these last two sections, especially where the speech is converted to text, we have some natural language processes or text preprocessing that is applied before we eventually do the final prediction. And prediction could be in the form of generating the next word or generating another speech and things like that. So, for example, if you have your bank app and it has a chat component to it, sometimes it could tell you, do you want to ask a question using speech? Or you may say a speech button, maybe like something like this, where you could click and talk, and then it responds to you in words. So those words, it's a form of prediction that it's predicting the next word for you. So it starts with, if you say, define machine learning. So it goes through all this processing. Again, I'm not talking about the bank app. I'm just talking about maybe you're using the voice portion of ChatGPT. What is machine learning? So the first thing it does, it will obviously understand the text, do some proper processing and things like that. Eventually, in the decoding portion of it, it says machine learning. So it starts with machine, then it goes through the training data that it has already understood to understand what could be the next word after machine. So it predicts learning. So, and then it takes machine learning, or it takes learning and predicts is. So machine learning is defined as this. So that's what we call next word prediction. Another example of next word prediction is if you're typing on your phone and maybe you say, I am, and then you look at your keyboard on your phone, you see 3 suggestions: happy, hungry, sad, something like that, for example. So that word that always shows after you type a word is a form of natural language processing where we're predicting the next word. All right, let's go to natural language processing now. So what is natural language processing? Is a field that enables computers to understand human language. before I continue, I just want to mention that it might get a little bit complicated in this presentation. But if you just follow me, I think you grabs most of it. All right. So brace yourself. So it's a field that enables computers to understand human language. It's basically the intersection of linguistics, computer science, and machine learning. So you have intersection of human language, computer science, and AI. So that's essentially natural language processing. So some application areas of natural language processing is, for example, chatbots, like I just mentioned earlier, email filtering. Is this a real email? Is this a spam email? Text summarization. You could take a text and put on ChatGPT and say, summarize this text for me. These are some, applications of natural language processing. Smart assistants, sentiment analysis, language translation. So what's the pipeline of natural language processing? You first get your data. So now we're not talking about speech recognition. Now we're talking about text data, for example. You get your data, you do some processing, you do some feature engineering, you do model evaluation, and then if you want, you could deploy. So when I talk about natural language processing moving forward, I'm talking about text data, a data set of text. Now, what is text preprocessing? Before you apply this text into a model, you have to do a set of cleaning or steps that'll make this text in a good form that could be applied to this model. For example, things like tokenization, text removal, stemming, lemmatization, and things like parts of speech tagging. So I'm going to explain these concepts moving forward for you to understand it better. Okay. Now, what is tokenization? It's a text preprocessing approach where a sentence is broken into tokens, right? For example, a sentence saying, it is raining. You could do character level tokenization in coding or machine learning. When we talk about character, in coding, when we talk about character, we're talking about each individual letter. So this character level tokenization, it is raining, is where we tokenize each singular letter. Or we could do word level tokenization where it is raining. So the it is raining is broken into words or subwords where you could have it is, then rain and in, where this word is broken down. So this is this is what we call tokenization. This is important because we want to provide a structure to the computers. And also we want to attach some numbers to these words. Computers cannot work with just words. So even the speech that's converted to text, it needs to be converted to numbers. So machine learning is mathematical, right? AI is mathematical. So scientists have found a way to attach mathematics to text. And so you have to tokenize these words or these characters and then attach numbers to them and then pass it to the machine learning model. And it does its mathematical calculations and makes predictions. So another thing that's been done again after this is what we call, so after you've tokenized, right, we remove things that are not important to us. For example, punctuation, or stop word removal. So in this code, we have this text. We are learning natural language processing. So here we remove some punctuations, like things like full stop, remove these characters that we see over here. So we are learning natural language processing. So this is removing things that are not important to us. Now, this is stop word removal. For example, sample text that says Geeks for Geeks, a computer science portal for geeks. So here, we remove the stop words, things like these signs or this question mark, or this comma you see over here. So things that are not important to us, we remove those things. Then there's what we call stemming and lemmatization. In stemming, what you're essentially doing is you take, so for example, you could say things, let me give you a sample sentence. You say, change is constant and change is happening every day. Now, we could, okay, let me say change is constant and changes happen every day. So you can see in that word, we have two change. We have one change and we have changes. So in your pre-processing step, one of the things you do is what we call stemming, where the two words change and changes are stemmed. We do stemming where we convert them to a singular stem. So when you have change, when you have changer, changes, changing, you convert it to what we call CHANG, right? Because this is something that's common amongst all these different forms of this change word. And then lemmatization is where we actually convert this word to something that actually makes sense. CHANG is not really an English word. It could be someone's name, but it's not an English word. Lemmatization converts that to an actual English word. So like you can see here, change, changer, changes, change, changing is lemmatized to just change. So that is some of the pre-processing you do in natural language processing. After you've done all this cleaning, stop words, punctuation removal, lemmatization, stemming, the next thing you want to do is what we call feature engineering. And why do we do this? Is because modeling only works with numbers. As I proceed, you understand what I'm talking about. So feature engineering, one feature engineering approach is what we call word embedding. So you give a computer a sentence, I am running. It has to embed that word in numbers to be able to work with it, right? Computers only work with numbers. Now, what embedding as an NLP feature engineer is essentially transforming raw text data into numerical representations that machine learning models can use to make predictions. And there are three common types of word embedding. We have one, what we call frequency-based embeddings. We have prediction-based word embeddings, and we have what we call contextualized word embeddings. So like the name implies, when we talk about frequency, we talk about how, occurrence, how many times it occurs. We'll talk about this frequency base. We'll talk about bag of words, TF-IDF. We'll also talk about what to vec. And then we'll also talk about contextualized embeddings. So before I go into frequency based, there's a very common approach to word embedding, which we call one-hot encoding. So let's say in a data set, you have a feature that is, you have a feature like level, called level, for example. And then the level can be low, medium, and high. And in that data set, most of the value, all the values for each patient information in that data set is either low, medium, and high. You have to convert that to numbers, right? So we could use something like word embedding, where each word is given a number. For example, low, medium, and high could be 0, 1, 2. So where low is 0, medium is 1, and high is 2, right? So this is an approach to encoding or embedding, where we convert these text words to numbers. So it's not a very efficient approach, because what you can see here is in this group of words, we have cat, mat, on, sat, the. This is the vocabulary, right? Now, let's say we have a paragraph of 1,000 unique words. That means each word will have an embedding that also includes for example, here, we call this 1, 2, 3, 4, 5. We have a vector. I don't want to use too many terminologies. So the here is a vector with 5 items, right? And these words, the cat sat. Okay, let's say the word was the cat sat on the mat, right? We convert each of these unique words that are important to us to a feature. So imagine this is a data set, right? So the features are cat, mat, on, sat, the. So if you have for example, a paragraph that has 1,000 unique words, you have to create a feature space of 1,000 unique words. And then because the occurs only once here, so you have one. But then the is represented as 00001. So imagine you have 1,000 unique words, and you just want to encode D. It will be 99 zeros. I mean, sorry, 999 zeros and one unique, and one for the. So this, if you use this in a machine learning model, this could be very computationally expensive because the computer has to represent each of these unique words, and it's so large, right? So this is not a very efficient approach to word embedding, converting words to numbers. So let's look at frequency-based embeddings. So there's what we call, for example, bag of words. So for example, you have a data set and you ask it, you tell it, this small dog is cute, right? Now, that we first do some text preprocessing where we tokenize those words, the small dog, cute, cat, things like that. And then we remove the stop words and words that are not very important to us. And then we're left with something like this tokenized words. So small dog, cute, cute cat, cute dog. Let's say these are 3 sentences, in the paragraph, right? Now, the unique words are what we make features, like you can see over here: cat, cute, dog, small. Now, what you can see here for the first sentence, we have both small and dog showing. So we get 1, 1. It's similar to what we the one-hot encoding, but this time around we could look into 2 words being together, right? So small dog, dog and small, small dog, 1, 1. Here we have cat, cute, cute, right? So cute, cute cat. So cute is occurring twice and cat once. Cute dog. So cute dog, 1, 1, right? So cute now gets the embedding of, this small dog now gets the embedding of 0011, right? So this is what we call bag of words. So this is a simple approach, but it ignores the order of the words. So order is important because, for example, if I say, I went to the riverbank, and I also say, the bank is open today. If I use this approach, it's look at bank as the same thing in both sentences. So it doesn't understand the meaning of both words. We can see bank in both examples mean different things. One is by the river, or another one is an actual bank, right? So if you create a model using just bag of words and you make predictions, it's going to give you sentences that, are crazy and, doesn't make any sense. And then another one is what we call bag of n-grams, which is like bag of words, but rather we have our sentence, and the n determines how the tokenization is going to be, right? So it could be unigrams, which is 1, bigrams 2, trigrams 3. So here you can see unigram, which is 1 each word, 1, 2, 3, and then we create a feature of data sets which with these words. So this is n-gram. So if n is 1, then you have this. If n is 2, and if n is 3, you have these. So this chosen, the n you decide becomes the features you have, right? So here we have, in this bag of words, we have each singular word becomes a feature. In these n-grams, instead of having just each word become a feature, we have n-grams, which is the n you decide will become these features you have over here. All right. So again, this lacks semantic understanding, and it can struggle with data sparsity and high dimensionality. Because of time, I'm going to move faster. Another approach is TF-IDF. I'm not going to talk so much in detail into this. It's essentially a mathematical way to come up with, if you look at this image, set of numbers that represent sentences. So again, it treats words singularly. It doesn't really understand the meaning or similarity between this one. So that was frequency. Now we talk about prediction-based. So rather than just counting the number of occurrences of words, we could actually use a machine learning model to come up with numbers that represent words and sentences using a prediction approach. So it's going to predict, excuse me, these numbers. So it represents words as dense vectors, and it also captures meaningful relationship. So for example, I have a first word, second word, third word, and then I pass it to a model, and then it predicts these numbers for me, and things like that. I'm going to show you an example eventually. So one example is what we call word-to-vec. So people who are a little bit familiar with machine learning and natural language processing, you may have heard of what we call word-to-vec. So it's word to vector. So it converts word into numerical vector. So a vector is just, how do I explain it in a very simple form? It's just a group of numbers, right? It's like, let's say, for example, I take the word dog, and that dog can have multiple numbers that represent that word dog alone. So you could say that's a vector. So word-to-vec, prediction-based, capture meaning and relationship with other words and context. So for example, if I have, excuse me, if I have a word in the middle, which is given as t here, the word before t-1 and t-2, and then the word after t+1, t+2, I'm trying to predict this middle word here, and I'm using what we call word-to-vec. Or I'm taking a singular word, and I'm trying to predict the words before it and the words after it. I'm going to show you a detailed example of this. So in word-to-vec architecture, there are two approaches where we have the CBOW, continuous bag of words, and the skipgram. So in CBOW is where we take the surrounding words and try to predict that middle word or a particular word. In skipgram, we're taking that middle or particular word and try to predict the surrounding words around it. So again, these are some limitations. As I mentioned, bank in River is the same thing as bank in River Bank and Money Bank are all, they're not, it doesn't really identify the differences. I'm going to move further. And then, so that's prediction. That's an example of prediction based. And there's what we call contextualized embedding. So if you're familiar with using large language models like BERT is, it's like ChatGPT, right? But this is BERT. The job of BERT is not to predict the next words like you. All it does is to understand the words or the context in your text. So BERT can also provide numerical vectors or embeddings that capture the meaning and relationship in terms of words around it, in terms of what around a particular word. So I'm just gonna very briefly, I have this input sentence. My dog is cute, he likes playing, right? So BERT has been trained on a very massive data set, right? A data set that comprises things like dictionary words, what's this thing? I don't remember the name. News, so many different things. It has been trained on that very massive data set. And so it has what we call weights that it has come up with, basically some mathematical representation that it has come up with that it can say, this is how I understand all this large data that I've trained myself on. So, and BERT has its own, what we call tokens or token embeddings, right? So if I pass the sentence, my dog is cute, he likes playing. And I pass it to Bert to apply what we call token embeddings, where each of these singular words will be given a unique number, right? So it will be given a unique number, excuse me. And then it does what we call segment embeddings. I'm going to show you an example of this thing. So segment is just, it's trying to segment some of this text, right? So for example, my dog is cute. He likes playing. We can see these are two different sentences. So one segment could be my dog is cute, as you can see represented by A, and then he likes playing is another segment, which is represented as B. Then there's what we call position embeddings, which is basically trying to understand the position of these words. If I give the example of, sorry, do I have a message? Okay, I don't. Okay. If I give the example of riverbank and money bank, right? So, excuse me. So Bert will try to understand the context of this using its tokenization, using its segment embeddings, using its positional embeddings and things like that. I'm going to show you a very nice visualization that explains it. So in BERT, essentially, these words are embedded, they're converted to numbers. And then, so you can see here positional encodings or embeddings. And then it's passed into what we call an attention layer. Now, I'm not going to go very much detail, and I'm going to go very fast in this presentation. But essentially, a transformer has what we call an attention layer, and it has other layers as well. Attention layer essentially tries to understand the relationships between words. For example, it is a car, and another sentence, it is a dog. Now, the word it, what should it pay attention to? What does it relate the most to? So it is a car. In the first sentence, it relates most to a car. In the second sentence, it relates most to dog, right? So you can see it should pay attention the most to car in the first and pay attention the most to dog in the second. And you can see those it has two different meanings depending on the context in which you're looking at it. All right. So I worked on a paper many years ago, last year, where I tried to use BERT. What I'm trying to do here is predict patient biomarkers. So patients that have gone to the hospital to collect their biomarker values. Biomarker values is things like blood pressure, BMI, their cholesterol level if you have heart conditions, or glucose level if you have diabetes. Glucose level is HbA1c. Why I'm showing you this is to just show you this embedding. So I collected data before COVID and data during COVID, right? And then I provided embeddings using BERT, specifically a type of BERT, right? So age embeddings. So for example, this patient here is 45 years old. So I applied BERT embeddings to that for age 45, right? So before COVID, they were 45. After COVID, they were 46 the next year. And their gender, let's say 0 was for man. So if I use gender embeddings, I have all zeros, right? They didn't change their gender. Segment embeddings was 0 before COVID and 1 after COVID. And then we also have positional encodings, which I didn't really show here. I just wanted to show you an example application of this. And then I generalized, I came up with my finalized embedding. So each of these embeddings are added and things like that. All right. So that's just understanding the space of embeddings. Now, there's what we call sequence modeling. Sequence modeling is a machine learning technique used to process and analyze data where the order of elements is important. For example, things like text, speech, or time series data. So I got my data, I did all the pre-processing, I converted it to numbers. Now I need to understand the sequence of that data. For example, here, I've come up with my finalized embeddings. I need to understand the sequence of this data before COVID and during COVID. How does the before COVID biomarkers change during the COVID, right? So there's a sequence. Is it increasing? Is it decreasing? Things like that. So that's what we call sequential modeling. Now, there are existing sequential models out there. So we have things like RNN, which is what we call recurrent neural network. We have things like LSTM, which we call long short-term memory. We have GRU, which is gated recurrent units and transformers. So this is how much sequential models have changed. So they started with RNNs, they went to LSTMs, which is, you can see it's more complicated. They went to GRU because LSTMs were taking a lot of computational time because of so many calculations they had to do. They came up with GRU, which tried to summarize this LSTM in a certain, much more simpler structure. And then they now went to transformers, which you see over here. Recurrent neural network, which is this first one, they process text word by word, and then they pass the hidden state. I'm not going to talk much because of time. I'm going to skip most of these things. But essentially, you take, excuse me, you take each word, you do some computation on it, you pass it to the next. So the next word will be passed into this new computation, and the word before is also passed into this computation, and it's passed to the next. So it passes to the next word in the sequence. So this apple pie is used in computation. These previous two words are also used in computation. So that's, trying to use the previous to inspire the next or to predict the next. So I'm going to skip this part, which is talking about some challenges with using things like RNNs and things like that. There's what we call exploding gradient and vanishing gradient. I'm going to move in straight to the transformers, which, excuse me, came up in 2017 in a paper called Attention is All You Need. It uses what we call self-attention, and it doesn't use recurrence. Like it doesn't, like the GRUs you see over here, where the previous word is implying the next. So so these other ones are like a sequential approach. They use the previous one to predict the next, previous one to predict the next, things like that. But in transformers, we have what we call parallel execution. So we don't have to wait for a previous word to finish. We can look at the words in a parallel form. So these are some terminologies in transformers, which I'm not going to go into much detail. Things like what we call query, things like what we call key, things like what we call value. So transformer attention mechanism, which is this middle portion you see over here. This middle portion you see over here is this whole thing you see over here. So as you can see, Q, K, and V, right? These are passed. Q, K, and V are gotten from the data set you've done cleaning, you've done embedding eventually. So this is that data set is converted to some set of numbers given as Q, K, and V. And then they are passed into this attention layer. Some mathematical applications are being applied, some scaling, so it doesn't become too big, some masking, and then some what we call softmax, which may have been captured in previous teachings in this class. And then this attention layer could be multiple attentions, like you can see in this image here. This is just one. You could have multiple attention. The more, maybe the better, but also the more could be very computationally expensive. And then you concatenate this multiple. And then we have what we call a linear layer where you could actually do predictions of the next one and things like that. All right. So what essentially is this attention? Anybody that talks to you about transformers, something they'll really talk about is attention, right? Attention, is where the model is asking which words are important for predicting this word. Example, the cat sat on the mat. Cat relates very strongly to the word sat, right? Also, mat also relates very strongly. Now, so this is essentially the intuition behind attention mechanism. Now, for models like BERT or things like GPT, which is the understanding behind ChatGPT, right? BERT looks at how cat, for example, in this case, relates to sat and relates to the, right? It looks at both the front and the back, how cat relates to both the front and the back. But on the other hand, when we talk about GPT or autoregressive, it only looks at how cat relates to the one before, right? How does, excuse me, how does cat relate to the one before? All right. I keep seeing messages, so I tend to look at them. All right. It looks at how the ones before relates to the, to the ones progressively. So in BERT, what the meaning of BERT actually is called bidirectional encoder transformers, right? So it looks at both direction. And then GPT looks at autoregressive, right? How the ones before influence the ones forward. So there are some popular transformer models out there, as I just mentioned now. So BERT is bidirectional, and it's what we call encoder-only architecture. If I show you this previous image here of a transformer, where do I have that image? So in this transformer, we have two structures. We have this left structure called an encoder, and this right structure called a decoder. So BERT only uses this encoder, this side. And then your ChatGPT uses mostly these decoder. Now, what does that mean? If I pass a data to BERT, the encoder, what it does is try to understand the structure of this data or the context of this data. After understanding that context of that data, it passes it to the decoder. And the job of that decoder is to use that context plus some new data to be able to, for example, make predictions, right? So if I want to create a transformer architecture that uses, that takes an input, maybe a language, English language, and predicts the translation, I use an encoder and decoder. I pass the English word to this encoder. It looks at the English word, understands the structure of this English word, and then passes it to this. It takes the encoder, the language word, passes it here in the decoder portion, and it uses the understanding of the English word and understands the language word and sort of put them together and provides the translation. So for example, ChatGPT, you give it an English word, it generates something for you. So you can say ChatGPT is a decoder-only transformer architecture. But BERT doesn't generate something for you. So it's an encoder-only architecture. And you could have both. So let's continue. I wanted to mention that. So when I talk about encoder only, I'm only talking about the left portion, right? This left portion of it, of the code. ChatGPT, for example, which uses GPT transformer in the background, is a decoder only. And then we have what we call text-to-text transfer transformer, which uses both the encoder and decoder. For example, when you want to translate text from English to Chui or Chichewa or any other language. Now, again, coming back to that paper, I think I'm going to skip these portions because these are a little bit complicated. I'm going to skip this part. Here, I'm just trying to show you some mathematical foundations of these architectures. I think at 2 o'clock American time, I'm going to switch to the coding part of it. Essentially, I want you to keep this picture in mind. So you may have learned some things about deep learning and things like that. This is a very common diagram in what we call feed-forward neural network, which is a deep learning architecture. Essentially, you take your input and feed it forward. What does that mean? Let's say I have a data set that has five features, right? Now, the features are the column names, right? And then I have each sample in that data set. Let's say the first one. So let's say we have patient information. And then the features are biomarkers like BMI, blood pressure, things like that as the features. Now, each patient has their own biomarker information, right? So those five, so let's say I take patient one and I take their features or their vector of features, right? I pass it here. So X1 maybe is BMI value for patient one. X2 maybe is LDL cholesterol value for patient two. Till the fifth feature. So for the first patient, I pass it inside here. Now, each of those values in deep learning architecture are multiplied by what we call weights. So weights are things that could help us understand the data set. So for example, if I pass in their blood pressure of let's say their blood pressure, I don't remember the blood pressure. I did that data that study a long time ago. So let's say they have a blood pressure or BMI of 300 something, right? Now, this weight is multiplied. So at the very first start, when the deep learning or feed-forward architecture starts, these weights are given a random value, or maybe 0, for example, or something. So each of those input values are multiplied by these weights, right? And then after the multiplication, we have what we call weighted sum. So we add up all that. We also add what we call a bias, right? And then all that value is passed into what we call an activation function. You may have heard of it in previous classes. An activation function is just something that provides a shock or a surprise to the values that the things are passing in. They convert sort of this linear process to something that is a lot more complicated. So for example, what's a good one I could give? I don't remember anyone right now, but let's say if this y in is 0, maybe that activation function will say, okay, if I get to 0, I'm going to give out a 5. If I get to 1, maybe I give out a 10, right? But then it could also say, if I get a -1, I get to 0. If I get to -2, I get to 0. So anything that this y in gives that is below 0, it's a 0 automatically. Anything above will multiply by 2. So that's some sort of activation function. It provides this change, this nonlinear transformation to whatever I pass in here. All right. So I wanted to show you, before I proceed further into the really complicated depth, I wanted to just show you this Word2Vec and give you an example, a pictorial example, so you could understand the embedding process. Now, so I've gone very far. Let me come back a little bit to make it much more easily understood. So Word2Vec, we talked about predictive embedding. We have words and we're trying to predict their numbers, right? So let's say I have a couple of words here, words like battle, horse, king, man, queen, woman. Now, these words we see over here, let's say we provide some sort of properties to these words. Let's say the properties we provide are words like authority, event, has tail, reach, gender, right? These are some properties we provide to these words. Now, these properties that we see over here, we could use these properties to define these words we see over here. So for example, a battle is not an authority, so we give it a value of 0. But it's an event. It has a value of 1. It doesn't have a tail. It is a battle is not rich, it has no gender, right? But on the other hand, a horse has a tail of 1. It has a tail, so we give it the value of 1. A horse is not an event, it has 0. A horse somehow has some sort of authority, so we give it a value of 0.01. Now, a horse could have a gender, right? We'll give it 1. Now, if we represent these things in this way, there's a way we could actually come up with a mathematical understanding of these words. So for example, here, if I look at king minus man plus woman, if you actually do this calculation, you have what we call queen, this queen over here. So 1 minus 0.2 plus 0.2, right? Will give you the value of 1. 1 minus 0.3 plus 0.2 will give you the value of what? 0.9. Which is approximately 1, right? So if you actually do these mathematical calculations, you'll be able to come up with some understanding of text. So computer could look at this and say, okay, if I do king minus man plus woman, then I'm able to get the result. This is equals to queen. So this is sort of the intuition in which computers use or try to understand or try to assign numbers to text. But the problem with this approach is there are too many properties. How can we know the amount of properties we apply to capture to capture the meaning of a word? So we could have 6 million properties. They're countless. So that's why we come with the predictive embeddings. It's a prediction approach where we don't have to use our hands to craft these properties. And they are learned during the neural network training. So the approach is we take a fake problem, we'll solve it using neural network, and we'll come up with some embeddings as a side effect. I'm going to show you what this is. So let's say we have this. This is a text on something that in India. It says, "There lived a king called Ashoka in India. After Kalinga battle, he converted to Buddhism. This mighty king ordered his ministers to put together a peaceful treaty with their neighboring kingdoms. The emperor ordered his ministers to also build stupa, a monument with Buddha's teachings." So our problem here is we have king, and king, we have Dash ordered his ministers, Dash ordered his emperors. So what we're trying to predict, remember, is what to vec, right? We're trying to predict king in this case, right? And this is the CBAL, continuous bag of words, if you remember. We're trying to predict this king. We're trying to predict emperor. If you look at this text, we have the king ordered his ministers. We also see emperor ordered his ministers, right? So we come up eventually with embeddings. If you look at these two embeddings, you can see they are very similar. 0.7, 1.2, 3.8 are the same, but it's just 0.4 and 0.5 that are slightly different. A king is an emperor, right? So wherever there's a king and wherever there's an emperor in this text, we can see they are basically almost doing the same thing. And so this is some sort of, what do you call it? Embeddings that's attached to this king and emperor, and they're very similar, right? Now, what I'm trying to show you here is the continuous bag of words approach, where we have our training samples. Now, we're taking the environment of words to predict a singular word, if you remember the image. So how we're doing it is we're taking lived A, and we're trying to predict there. So the next two words predicting the one before, lived A, there, a king lived, king called A, right? So lived A, we're trying to predict there. So in our training samples in this continuous bag of words, where we want to provide embeddings for these singular words, this is how our training samples will be structured, right? So here we're saying we're trying to predict, excuse me, king here. And we say, so what we do, we take the whole vocabulary of unique words and we put it in this structure, right? Ordered is what we're interested in. So ordered get the value of 1, his gets the value of 1. And then if you remember that picture where we talked about activation function and weighted summation, that's exactly what's happening here, right? And then we make prediction here, right? And this is king. King has the value of 1. All right. Now, this is the same image, but here we're just trying to predict emperor. If you remember, in some of my early teachings, I told you about backpropagation, which is where we make prediction and we look at the difference between the actual and the real, and then we go back, we propagate backwards, and then we continue like that, right? We go back, do the training again, make predictions, check the difference. If it's very bad, we go back again, check again, and things like that. Here, what we're doing is we took ordered his, and we did some mathematical calculations, which activation function, weighted summation. We made prediction here. In reality, right, the actual was supposed to be emperor, if we're considering this scenario, right? Ordered his, and we're predicting emperor. So emperor is what's supposed to be predicted. We should get the value of 1. But in the first instance, when we went the feed forward, when we went from the left to right, we got emperor as 0.1. And then we look at emperor 0.1 and the actual as 1. And we say, this is not very good because the real is supposed to give us 1. So we go back propagation, back, and we go back again. So this continues till emperor gets a higher value. Now, that backpropagation process is what we call optimization. Now, in this case, let's look at the king ordered his scenario. Now, these weights that lead us to having the best output of what the actual value is, the best prediction, these weights are these numerical values that represent king. Now, W1, W2, W3, W4 is what become the number that represents king, and that becomes our embeddings, right? Embeddings are just the length weight. So this is word to vec in the continuous bag of words approach. So when you want to represent king, you just give it this. So king, that will be eventually passed to the machine learning model for natural language processing and everything, will just be these numerical numbers. All right, I'm going to skip this part. So I'll just talk about this image. Eventually, when we do all this predictive embedding approach, we're able to represent words in a vector space, right? In a dimensional space, my bad. So we could see here, king and queen are related to each other, but king and man also are related to each other. But you can see the difference, the distance between king and queen is much larger compared to the distance between king and man, you can see, right? The same applies to queen and woman. Here, this is, you can see that Spain is very close to Madrid. We can see when we do this mathematical embedding approach, what we see is Spain is very close to Madrid, Italy to Rome. These are just their capitals. All right, I'm going to skip this part. I have too many slides, so I'm going to skip all these parts. And I think I'm just going to go to the coding. But before I go, I wanted to show you something just to highlight this concept of positional encodings as much as you can. As I mentioned earlier, a transformer is encoder, and then you have decoder. All right. Okay. I wanted to show what position, in the transformer architecture, how positional encoding works. So we have a sentence that says, no, it is good. And we have another sentence that says, it is no good. Now, these two sentences have exactly the same words. but they mean totally different things. This one is a positive sentence, right? And this one is a negative sentence. How can we apply this contextual understanding to so the model in its eventual prediction can really understand that these sentences mean two different things. If I use the bag of words approach and bag of engrams approach, these things would mean the same thing, right? But now, and also sometimes if I use the word to vec approach, it will still look at it as the same thing because all it's doing is just predicting the surrounding words, right? But now in the transformer approach, in the BERT approach, so we have two forms of embeddings. We have the normal embeddings where we talk about token embeddings and things like that. And then we have what we call position embeddings. Now, this diagram might look complicated, but just follow me. You understand it. Now, we can see in the transformer paper, we have some mathematical formulas which are being used for the positional encodings. So I in this situation is represented, the sign is this way, the cos is this way. When I is 1, the graph is a little bit different. When I is 2, the graph is even more different, right? This is what we have in here. Now, excuse me. In the first word, right? Let's say, so we use the structure. So no, let's take the first word no and the first word eat here, right? Let's take them. In the first scenario, we see no for the first word here is is given as this blue, right? Eat is given as this blue here. The next word eat is given as the green. The next word here is given as this. Is given as this, and no is given as this, right? So we're looking at this horizontal vertical line here, right? So blue, green, orange, red, and you can see this final one. So this is essentially a way in which these positional numbers are applied to these words to make it to identify the differences between. So after this sort of encoding is applied to these words, that is also added to all those original embeddings that we had, token embeddings and things like that. And then it's passed to the attention layer. All right. I'll encourage you to read about these things. They're really exciting things. Here is what we call, this is just a visualization for the transformer. You can see the cat drank the milk because it was hungry. The cat drank the milk because it was sweet. What does eat mean in this sentence? Eat in this first sentence, because of hungry, relates to cat. Eat in this sentence because of the word sweet relates to sweet here, right? So if you visualize this using what we call BERT V's, you can see eat is relating more to cat because it's the most highlighted, right? For this eat word and milk here. All right. I'm gonna skip this portion because of time, and so Tabri doesn't get mad at me. And then this is just a simple visualization that I wanted to show you. If you go to this link, you could, and you do some little bit of reading on transformers, you could really enjoy this thing. So we talk about embeddings here, things like token embeddings, positional embeddings, attention layer, masked attention, things like that. That'll be very useful. All right. That concludes this presentation, but I'm going to go to the code examples now for you to see. The code is just very simple. I know I've talked a lot on very complicated things, but I just wanted to show you some tokenization approaches here. Now, if you want to do some tokenization and text preprocessing, that's what I'm showing you here. There's this library called Natural Language Toolkit, which you could use. Essentially, what I'm doing here is tokenization. I'm using tokenizer from this NLTK library. I have these words. So this is, rather than just speaking a lot, let me ask the audience, what type of tokenization is this? We talked about character. We talked about word. We talked about subword. Can somebody help me? You could type it in the chat. What type of tokenization is this? Okay. I think what I've taught me have been highly. Can you hear me? Hello?
Yeah, we can hear you.
Okay. Thank you. Thank you. All right. Thank you, Mohammed. So this is word tokenization. So I have this sentence. It has this is an example paragraph. It has multiple sentences. So I just tokenize by singular words. Here is stop word removal, right? So this is an example paragraph. It has multiple. So some stop words include things like is, an, it, has. So those words don't really give any information. So here I just did what we call stop word removal, lemmatization. If you remember, I have paragraph, multiple sentences, punctuation like commas, periods. Commas is not an actual word, so comma is an actual word. Maybe commas is an actual word, I don't remember, but this is just converting these words to actual words. And stemming is just chopping. So here you can see sentences. Here I just converted it to singular words. So here, what am I doing? I'm just generating some sentences. So here is just showing some sentences and the equivalent of the cleaned words before the embeddings, right? So this is just a summarization. So I have the actual words, I clean them, put them in tokens, remove the stop words. So see this whole sentence here. If I remove the stop words, are just three major sentences that give information. And then lemmatization and stemming. Instead of plain, I have play for stemming. This is essentially, again, showing the same thing. This is what we call bag of words, like I did before. So I I downloaded a data set, and then this is just a matrix of the bag of words. So how many times a particular word is occurring is given by this. Okay, so this is this is the word here. The cat sat on the mat, right? And then this is just the representations of this. So because this whole document here has a number of unique words, that's the feature matrix. I mean, the feature vector we see over here, right? So this is how many times these unique words are occurring. So 2 here could represent the word the and the here. All right. So that's bag of words. Here is term frequency IDF, which I didn't really explain because I didn't want to go deep down into the details, but it just essentially comes up with some set of numbers that represents the words you have and things like that. So for example, here we can see the has the equivalent word of 0.5519 for the first document, the cat sat on the mat, right? So sat has its equivalent number and things like that. So also you can see mat and cat, because they're very close to each other, they have almost the same actual values. I'm going to end soon. What else did I have in this code? This is again tokenization. Here is what we call, remember the bag of n-grams here. So I have a sentence that says, natural language processing is a subfield of linguistic computer science, an AI concerned with the interactions between computers and human natural language and things like that. So here is a code that all I'm doing is bigrams. Bigrams means two. So n-grams, bag of n-grams is, splitting these tokenized words into two, right? Natural language, right? And then it moves one step. So natural language, then it goes to language, then it starts from language now, language processing, right? Like you see here, then it moves one step again, processing and something. This is taken as a, excuse me, an item, right? Here is trigrams, natural language processing, and things like that. So it's three, right? So into three. Here, it's just calculating the frequency. So for bigram frequencies, how many times does comma and end occur, right? 3 times. NLP occurs 2 times, things like that. Most of them are 1, 1, because 2 words might not occur very often. Here is just frequency, counting the number of frequencies for 3 words that are categorized together, and things like that. What else do I have here? Excuse me. All right. Excuse me. So I know I've talked so much, but I wanted to show you how an example. This is a sentiment analysis task where you're trying to classify text. Some applications of sentiment analysis we see, for example, during the COVID, how people were typing on Twitter, like their sentiments they were passing, like were they angry and things like that. So people, machine learning experts, went to take a lot of the text from Twitter and they use it to train sentiment analysis models, right? So this is an example of a sentiment analysis classification data set. So I have a very, very slow moving, aimless movie. That sounds like a negative sentiment. So in the data set, it has a 0 here. Not sure who was more lost, the flat character, something like that. So this sounds angry. So it has a value of 0. The best scene in the movie was when blah, blah, blah. It has a sentiment of 1, meaning like a good this thing. So this is how the data set is in a sentiment analysis classification. And then you obviously do the tokenization, calculations, and things like that. Eventually for prediction. So when you do all the tokenization and everything, you process your text into this form, right? So a very, very, you can see A is not showing here because the stop word, I don't need it. It's not important. A very, very, so maybe I just take very, right? 1 very. And then because it occurs 3 times, it has a frequency of 3, right? But eventually, after all that stop word removal, my processed text is this, right? And this is eventually what I pass into the model. But remember, you have to always split your data set between test and train. So before I even do anything, I have my training set and I have my test set, which is 20% of the data. And then I can now do, so here is just showing you the shape of everything. And then I can now make predictions. This is a confusion matrix of how the model did between, first of all, it has an accuracy of 0.74, which is good. It could always improve. This is a confusion matrix where I have, it's trying to predict the sentiment, right? So it's just trying to see so here what it's saying, and I think I've touched on this, what this is saying is when I'm predicting that the sentiment was negative and it's actual negative, I got it 49 times. When I predicted negative and it was actually positive, I got it only 12. I failed 12 times, right? Here, when I predicted positive, it was actually positive 62 and vice versa, right? Predicted positive and it was actually negative, which is a failure. I got into it 7 times. So this is kind of like a good confusion matrix, but it could always be improved. And again, I think it ties to this 0.74 that we have accuracy we have over here. There's something I wanted to show. This is so we have Word2Vec. We also have what we call Glove-E embeddings. So Glove-E is different from Word2Vec. Glove-E of Glove-E uses some sort of globalized embeddings, right? But when you apply Glove-E and you apply things like PCA, which I've talked about previously, you take this large vector space of features and you just convert it into if you want to visualize two-dimensional features. So you could have 1,000 unique words that are features, and then you're essentially just converting it into two features that could describe all those features, right? To a great extent. When you apply PCA and you do visualization, and you apply PCA on these embeddings, right? You can see, and you visualize it, what you can see here is these words have some sort of clustering. They come together where they have some sort of similar meaning, right? For example, you can see boat, airplane, car, train. These words are very similar to each other. They are automotive, right? They move. They're used to carry people. Excuse me. Broccoli is just on its own, I think, because people don't really like broccoli as a vegetable, so it's very far away. You have pizza, banana, sushi, apple. These are somewhat similar to each other, and so they're related to each other. Then here we have animals: elephant, lion, cat, dog, tiger, and things like that. Here we have occupation, right? We have doctor, artist, scientist, teacher. I wonder why engineer is far. That doesn't sound very encouraging to engineers. I'm just joking. And then you have emotions: happy, angry, excited, sad, calm. These are also quite clustered to each other. So these are some really cool things you could do with in natural language processing. And I think it's a very exciting and emergent aspect of machine learning that is constantly growing. You could just get a random data set, or if you go to things like Kaggle, you could see different data sets, and you could do very nice visualizations like this before you eventually do your modeling. This is another visualization here. This time around, we're visualizing sentences, not just words. Sentence embeddings, right? Dogs are also popular. Cats are popular. So these two sentences are quite similar. And so they're around the same category. Data science involves machine learning is quite similar. Natural language, so they're quite similar. So they're around the same space, right? And things like that. So this is what I really wanted to show today. I know it's a lot of things that I've talked about, but it's just to inspire you and just sow that seed in you to explore. Machine learning is very fun, and I think anyone can learn it. And I encourage you to pursue it and learn it. Thank you.
All right. Thank you, Trustin.
Yes.
This has been a wonderful session. And thank you for keeping it short so that we can release people to go. All right. So a few housekeeping announcements. We are at the end of the lectures. And so lecture 9 completes all the lectures that you needed. The next stage is projects. So we're going to give you projects, and your teachers will come and demonstrate the projects and give you the notebooks, and you will go and practice it and submit the project. So for our next 2 meetings, we are just going to do projects and practice. We are going to give the certificates. Everyone is going to receive a certificate. But based on your attendance and the days that you signed, we are going to put the topics that you came for on the certificates for you. So if you came for all of them, you have all the topics on the certificates. If you came for just 2, you have 2 of the topics on your certificate. We have all the timestamps and everything that we need to be able to issue those certificates. So thank you very much for being a part of all the lectures. As we go forward, when you come, it won't be lectures, it will just be practice, and you will do the projects with the teachers. And then when you practice it and you're able to do it, when you submit it, then we give you a certificate of competence in that project. So thank you very much, everyone, for coming around. If you need any information from us, just email me or send a message. Alternatively, you can also go and watch the videos that you missed and then answer the questions that are in it, or send a summary of the things that you learned from it, and we can use that to mark your attendance. So if you missed any days that you didn't mark attendance, just go back to the videos, watch it, submit the questions that are in it. If there are no questions in the video, just submit a summary of what you learned from the videos, and we are going to use that to mark your attendance, and then we can put that on the certificate as well for you. So thank you very much for coming around. Just send me a WhatsApp message if you need any information, or an email if you need any information, and we'll get the information to you. All right, Trusting, thank you. I'm posting the attendance one more time. If you missed it all the time, then I'll give you some 2 minutes to grab the code, the link, and then have it. All right, see you all in 2 weeks.
Yeah.
God bless you. Bye-bye. Enjoy the weekend.
Thank you. Thank you.
Thank you.